So, this is 141. We're about halfway through. I'll have midterm grades coming out soon. There is no midterm exam. I'll just take the quizzes and projects done to that point and make a grade out of it. And we're going to talk about key hashing. And then I got some demos, including the one that came up at the end of last class when I said I did not understand the length extension attack. And we looked at a video, so I wrote a hands-on project so you can perform the length extension attack, which a student suggested, and I agree. That's what's necessary. So I can understand it, and I think it's probably the same for you. You don't really understand it unless you've actually done it. So, all right. So we're going to talk about message authentication codes and the things that are used to make them, including pseudo-random functions and some special kinds of hash functions. So anybody can calculate the hash, like a SHA or an MD5 hash. There's no secret value involved, but all that does is give you control of integrity. Then if you make a copy of the file and somebody calculates the hash again at the other end, they can tell if the copy has been altered. So that's something, but it does not provide authentication. It doesn't mean you know who the author was. Anybody could calculate that hash. So what we're looking for here are message authentication codes, and they're going to use pseudo-random functions. So a message authentication code has a secret key, and it provides integrity by running it through a hash function. So now you not only know that the file has not been altered, you also know that it was sent from the authorized person who holds the secret key. That's the idea. So now you get integrity and authenticity. So they're used in a lot of systems like TLS and IPsec. For 3G and 4G telephony, encrypt packets but don't use a MAC. And that means an attacker can modify the packets. They're causing junk. They can't forge data, but they can scramble data. And since there's no MAC, you won't know it's been altered, so you'll get static. Now, here's what a message authentication code should resist. You should not be able to make a forgery. You shouldn't be able to create a message and tag pair if you don't have the secret key. That's the idea. They call that unforgeable if I cannot find any forgeries. So here's the known message attacks where I passively collect messages and tags, which is what would happen if you're, say, stiffing a network that has these signed messages going by, and you try to find the key. All right, that's one attack. Another common one is the chosen message attack, which is the kind of thing that happened in WEP, where you can actually feed in data and it will sign it and send it off. So now you can choose messages, and it will put the tags on them, and then see if you can still derive the key from that. And you'd like to have a MAC system so strong that it can survive even this attack, because this is fairly common in practice. All right, and then of course, none of them are safe from replay attacks. If you record a message and tag, you can replay the same message and tag later and it will pass the test. So to prevent that, you would have to add an extra message number in each message, which then gets hashed. And in addition, that message number would have to be unpredictable, so it would have to be something simpler than just a counting number, but that would be one way to prevent replay attacks. All right, so you have pseudo-random functions. Now these are using a secret key to create apparently random stuff from a key and a message. And so key derivation schemes, that's what they are, right? The whole point of key derivation is you take a password and you're going to somehow create a apparently random cryptographic key out of it. So that's a pseudo-random function. It's not necessarily perfectly random in any abstract sense, but it is unpredictable. A small change in the key will change half of the bits in the output on average. That's the idea. All right, and you can also do it in identification schemes like challenge response, where the server sends you a challenge, like 16 random bytes. You add that to your password and hash it and send it back, and now run it through a pseudo-random function. And then the data on the wire looks random, so the attacker cannot deduce your password, but the server can reproduce the calculation and make sure that you get it right, and that proves that you know the password. So 4G telephony uses it, and TLS uses it, because TLS has the same idea. You do a public key encryption exchange, and then you send a secret through that, and then you use that to generate a session key. So it looks like it has no pattern. It looks like random bits, and it's fundamentally stronger than a MAC. MACs do not have to be as strong as pseudo-random functions. A Hmac is secure if it can't be forged. It does not have to look random. It just has to be unforgeable. So technically, it's a less strict criteria. So you can use unkeyed hashes, like the kind we've been using, like SHA-1 and MD5, and you can turn them into key hashes. All you need to do, for example, is put the key before the message. Key, this just means string concatenation. Take the key, then put the message, and hash that. This is essentially what CHAP does, Challenge Handshake protocol. Now, this might be vulnerable to a linked extension attack. I could have, if I wanted to have another message there, I could take the hash value of KM1 and just perform another round of the hashing function to add an M2 to it. So there could be a linked extension attack where I can construct another pair of forgery, another message with a valid tag from just this. So that's a weakness. And of course, that would affect SHA-1 and SHA-2, but not SHA-3. As we talked about last time, SHA-3 is not vulnerable to these linked extension attacks. All right, so here's there's another problem with it. You didn't add any delimiter between the key and the message. So if the key is 123ABC and the message is DEF, or the key is 123A and the message is BCDF, in both cases you have the same thing. So that's kind of an error, a weakness. It doesn't discriminate between the key and the message. So Blake and 2 and SHA-3 include a method where you add the key, and the key is handled explicitly and sensibly in the protocol, instead of just trying to ram the key into something that was not intended to be run with a key. But another fix, by the way, is to include something else like the key length here. The length, then the key, then the message. Now you know how much of it is key and how much of it is message. So here's the other one, is the secret suffix construction. If you put the key at the end and then hash it, now you can't do linked extension, because even if you know this, you can calculate this hash of M1K and M2, but what you need is hash of M1, M2K, and that's not the same. So this will prevent the linked extension attack. Now, if there's a hash collision, then of course the tags will collide too. If it's possible, if it's a linked extension attack, if this is the right length and that's done with just another cycle of the hash function, then that's an issue. All right, so there's an Hmac construction, which is the one that's specified. They're missing an I, that's why it's complaining. All right, this is Hmac is what's used by a lot of popular protocols. And Hmac looks like this. You take the key and XOR it with an outer padding, and then you take the key and XOR it with the inner padding. You prefix that to the message and hash it, and then you take another round of hashing with this in there. So the key is used twice. It's XORed with something twice to use different bits of the key. 2 rounds of hashing are here. So obviously this is a complicated construction that's not going to be subject to a message extension or any simple form of forgery. And the outer padding is just 5C bytes, and the inner padding is 36 bytes. I don't know how they chose those, but anyway, it has the effect of using different bits. In each case, flipping some bits to make effectively 2 separate keys here out of the input key. And that looks still pretty fast. You just have to go through some XOR processes and the hashing function twice. And it seems to be complicated enough to resist all these simple attacks. So it'd be very hard to create forgeries. Now you have to specify the hash function, which we haven't done. So you see HMAC-MD5 HME-SHA-1. Here's HMAC-SHA-256. Remember, SHA-256 works like this. Takes your key and your hash and compresses. This is the 8-match. This is the compression, where you go through the stages, and you use this compression function for SHA-256. All right. And so here's the way to evaluate how strong it is. The generic attack is to just try to mediate a hash collision in order for it to work. So you'd have to do 2 to the n over 2 calculations, where n is the length of the digest. This is assuming you don't have a shortcut like a hash extension attack, and that's a measure of how strong it is. So it's just the square root of the number of possible hashes, and therefore even 160 bits would probably be enough, and 256 bits is certainly enough. So they mention here, if n is larger than 128 bits, then the square root of that is 2 to the 64, which is a monstrous number of calculations, although barely possible, but anything much bigger is essentially out of reach. So that's a general idea. The Hmacs should be secure as long as they're at least 128 bits long, and all the ones that are commonly used are longer than that. So let's try a Kahoot. Take me a minute to get in. And we're in 7A. And there it is. Might be all we're going to get. All right. All right, so which system does not have a Mac? That was 4G telephony. Cannot tell when packets have been modified or damaged. All right, which one is the most successful against a Mac? The replay attack is very effective. Chosen message is much more difficult, but most of all of them are completely vulnerable to replay attack, and that's, of course, very easy to perform. All right, which hash is not vulnerable to linked extension? Yep, that's point of SHA-3. SHA-3 uses that different system where you you absorb all the data and then you squeeze out some of the bits, and that's not vulnerable to linked extension because the last step is different. All right, which system is vulnerable? Secret prefix. If the secret comes first and then the message, then you can just add more message after it in linked extension. The secret suffix is not vulnerable. If you have the message first and then the secret, then adding more message after that does not create a valid tag. The secret always has to come at the end. So linked extension will not create a valid tag. All right. Code B. Good. The faces, I think, doesn't care about the fonts, so that's fine. All right. So let's go back to here. All right. So we're going to create keyed hashes from block ciphers, and one of them is Cmac. So you can use this one here, builds it from a block cipher, SHA-256. Well, this one's done from a block. All right. That one's using a hash function. But let's go to this one. Here's the way you do it. Compression-based hash function. We talked about this before. You feed in message and an initial value to get a next initial value, and then again and again you compress and compress. And the final internal state, H, is the output. This is the compression-based hash function, which is the way most of them work. And so inside there, you've got a block cipher that encrypts it using the message block as the key, and then using an XOR feedback loop here to make it more complicated than just performing the encryption. So you can take any encryption routine and use it to create a hash function this way. And that's one way to do it. But the thing we're going to do here is that's what's going on. Compression functions are built on a block cipher. This is, Hmac uses only a block cipher, which is very simple. And the way it works is you do CBCMac. So your message goes in here. You have IV equals 0, and you just encrypt the message. The message is all this plain text, and you just keep the last block. Now, because it's cipher block chaining, every block is included. This block is used as the IV, this ciphertext is used as the IV. So the last block depends on every bit in the key, and that's it. This is one possible way to make a hash function. You've got a key here, and you ended up with a hash, saying here's your message. So that's one way to do it. A very simple system. All right, now the problem is, if you know the tag part here and here for two single block messages, you're going to see there's going to be a kind of way to combine these to cheat it, the same way as the other flaws with cipher block chaining that we've seen before. So in that case, I can then forge a tag. I can take two messages, and by XORing that with a tag I know here, I can create a forgery. I can create a tag of this message. So from other messages, I can combine them to create a new valid message, and that violates the plan here. I can forge a message in a tag. So that's a flaw in that system. So if you want to fix it, then what you do is you use the key K to create two different keys, and then you encrypt the last block with a different key. So this, I think, should say K1 and K2. But anyway, oh no, use K and then K, it doesn't matter. But the point is, this is essentially what that other construction did before, where you would XOR with different things. That's a way. As long as the last round is different, then you won't be able to combine two of these to create a third, for the same reason as secret suffix prevents it, because if you had a longer message, this one that's different would have to be at the end. And if all you know is valid pairs of message and tag, then none of them is missing this block at the end, so you can't add them together. So that's a way to fix CBCMac. And so here's the rule. If message fills the last block exactly, you use K and K1, XOR it here, and encrypt with K every time. And if the message padding is needed, then you use K and K2. That's the rule. That's what they chose. I'm not quite sure why they did it that way, but it has the effect that the last round is different, and that means you can't take any series of sniffed tags and messages and create a new forgery from them. So those use hash functions and block ciphers, but of course, as you might imagine, that is inefficient. Those were designed for other purposes, and they're probably more complex than you need. It would be better to design something that just meets the cryptographic requirements of a Mac without also meeting the requirements of encryption or hashing, and that's what we're going to do here. So that's Poly 1305, for example. This is intended to be fast, and it's used in HTTPS and OpenSSH. And what this does is it uses a universal hash function. A universal hash function is simpler and much faster than a cryptographic hash function, and it's not collision resistant. It uses a secret key and a message. The only security requirement is that if I have two messages, I'm never going to observe the same answer for the hash function from them, for a random key. It doesn't need to be pseudo-random. It doesn't need to scramble the bits. So by getting only what we need, you can make it more efficient. And so here's an example of that. Here's one that's used. It just takes a polynomial. You take the key times the message, and then another block of the message. I think it should be M2 here for key squared and M3 key squared. Yeah, it should be a 2 here. It's a typo probably in your book. But anyway, you take blocks of message, and you multiply each one by a power of the key, and then take mod P. That's a simple way to use them all and get a hash function created out of it that depends on every block and depends on the key in a nonlinear way. And this is good enough. You have to never reuse the key again. But because if you did use the key twice, then it would be like using the one-time pad twice. You'd have two examples encrypted with the same key, and you'd be able to solve this equation, so learn things about the key. All right, so here's one that builds a Hmac from universal hash function. All you have to take is you feed it two keys, a nonce, and a message, and then you take a universal hash using key 1 and a pseudo-random function using key 2 and the nonce, and combine them. That's a way you can create something that's going to have all the desirable features of both, and it's going to be much faster to calculate because this is a very simple hash function. All right, and you could use, I'm not sure, I'd use a pure pseudo-random function though, and that's the game. As long as you don't reuse the nonce, then, and these things are long enough, then that's quite secure, and that's more fast to calculate. Here's a Poly 1305 AES, uses AES over here, and that's considered to be very fast. Remember, AES was carefully designed to be very fast. So this is Poly 1305 is a universal hash, and that is one way to use Poly 1305 and AES together to create a message authentication code. Then there's one called SIP hash. This one is optimized for long messages, and if you have small messages, then you can do something much simpler called SIP hash. It only works up to 128 bytes. And what it does, this is a 15-byte message, so you have M1 of 8 bytes and M2 of 7 bytes, 1 byte of padding, 1 of 8 bytes. So here's 8 bytes, and M2 is 7 bytes, and you have plus 1 byte of padding. So you have 8 bytes here and 8 bytes here, and you just run it through SIP rounds, XORing in these keys, and these are constants, I think. Let me find out what the C is. I'm not sure I understand what the C is. Hopefully it's going to tell me somewhere. Nope, okay. You have to look at the book for the details of this one, but the point is it just uses these very simple operations of just XOR and this SIP round, which is something simple like that polynomial. I'm not sure exactly what it is, but the point is it's a special hashing routine designed to have just what you need for a message authentication code and work only for short messages. And like I say, it only uses very simple things, XORs, additions, and word rotations to make it fast. All right, so things that can go wrong, there can be timing attacks, verification. Never seem to be able to get the typos out. All right. All right. There we are. Okay. Yeah. All right. There. All right. So this side channel attack, of course, is where something leaks out. So this code, for example, if you're trying to do something efficient, this code will return more quickly if the first byte is incorrect. It's comparing a series of bytes. If the first bytes are different, it leaves, saying they're different, and it doesn't bother checking the further bytes. So this is the kind of thing you typically write to make code efficient, but if you won't want your code to have a timing channel, side channel, you have to write constant time code where it will always do every operation, even if it already knows the answer. You have to waste time to make sure that it always takes the same amount of time to do the calculation, or you'll have a timing channel leak. And so if sponges leak, remember, like the SHA-3 is a sponge, soaking up the data, and then you squeeze out some bits. If the internal state leaks, then you'd have a problem, and permutation-based algorithms would fail, and you'd then be able to have forgery, like SHA-3 and SIP hash. But compression-based functions, this would not change it, I think, because the different functions use the internal state in a different way. So that's an issue. These are things that can go wrong. All right, let's take a look at the other Kahoot, which is here. People, if Facius comes in. thought so. All right. All right. All right, a hash function that is not collision resistant. Universal hash function. Only has a certain mathematical property, but not general collision resistance. All right, which system is fastest for long messages? That's the Poly 1305 with AES. All right. Which one is fastest for small messages? That's the SIP hash. Good. And which one uses a block cipher, but for only one block? The Poly 1305 uses a block, the AES, but only for one block. All right. All right. All right. Those two people won before. Oh, now it's the other person winning. Good. Okay. All right. So that's it for the left. And I think I can go into the demo. Let me stop this recording.